Got 2 lemons in this bag and 1 lime in this bag. So we're going to pick 2 different fruit. If we pick 3 fruit, that'd be pretty boring because then we're going to get them all. So we'll pick 2 fruit just to kind of keep this simple. So the first time, what could happen? We could get a lemon, or we could get a lime. And then we're going to do it again, right? So what if that happens or that happens? We're not replacing them in the bag, and that issue of not replacing them is what creates a tree diagram with conditional probabilities in the first place. So what's the chance of getting a lemon? 2/3. So that's what you'd label with here. On your tree diagram, you should always have your percentages or your probabilities, whether they're in percentage form, decimal form, fraction form, whatever, on the branches of the trees. Yeah? So it's 2/3 chance of that. What's the chance of getting a lime on your first draw? 1/3. So now, once we move to this branch of the tree, something has already happened. That's the condition part, right? We've already drawn a what if we're up here? A lemon. So what's left in the bag at this point? 1 more lemon and 1 lime. So on the second draw, we could get, again, a lemon or a lime. I'm just going to put that on both of these here. So if there's 1 lemon and 1 lime left in the bag, then what's this probability now? Half here and a half there. Now if this happened on the first draw, if we immediately drew the lime out of the bag, there's not another lime left to draw, so what should I put for this probability? And this probability. Exactly. That should clearly make it the issue of conditional probability crystal, I think. So now, to actually find the probabilities of how many different outcomes are there here? 4, right? There's 4 different outcomes here. Well, not really, because the bottom one's kind of impossible because of that 0. But we'll think of it as like 4 outcomes, just to be general. This is a really simple example. But you want to multiply along the branches to get this. So what's this probability going to be of getting a lemon and then another lemon? Well, it's going to be 2/3 times 1/2, which is of course 2/6, which is 1/3, which is 33%. So we multiply along here, aren't we going to get the same thing? It still does 2/3 times 1/2, so I'm not going to write it out again. And then down here, what are we going to get? 1/3 times 1 is, again, 33%. 33%, 33%, and 33%. If you round them, add up to 99%. But really, am I supposed to round those kinds of things? No, aren't they these? I guess I really shouldn't write it like that. That's bad notation, but it's 0.33333333 continuing forever. If you put those all together, you of course get 100%. Okay, so this is 0% down here. So there's a tree diagram. So now let's ask some questions about that tree diagram before we go back to our example from yesterday that we kind of butchered due to me going too fast. So, what's the probability of getting 2 lemons? What's the probability of getting 1 of each? What's the probability of getting a lemon, let's say this, getting a lime given that you've already gotten a lemon? So once you have your tree diagram written out, it should be pretty easy, right? What's the probability of 2 lemons? Where do I look on my tree? Just the first outcome, so that answer is 33%. That's just the top. Probability of 1 each is 66% because that's 2 different outcomes added up, right? That's this outcome and this outcome. So that's going to be 66%. Remember, you read this and you need to know how to read this carefully. This is the probability of getting a lime given that a lemon already happened. So that means look where the lemon already happened, and the sample space is now limited to this part. So it's 50%. That's a little bit trickier, right? You can get that off the tree by thinking about just that limited sample space, or you can use the rule from before. Let's dress that rule up again one more time with this simple example. So let's call this event, instead of lemon and lime, because L and L is like too crazy, let's call this event A and this event B. Okay? So the general rule of multiplication that we learned yesterday that had this given thing in it is that the probability of, was it and or that ends up being multiplied? And. These are the good ways to remember these rules, little teeny rules of thumb. Probability of A and B, if they were independent events, it's just the probability of A times the probability of B, right? But are these independent events? Well, clearly not. When we take a fruit out of the bag, it totally changes the ballgame, depending on what that fruit was. So these are clearly very dependent events. So you can't just say A times B. You have to modify that second piece. It's the probability of A, and we're doing a multiplication here, aren't we? It's the probability of what? Of B given that A already happened. Okay? So you can use this on harder problems like we did on that one with the computer chips yesterday, which we're going to revisit now, to solve for the probability of A if you know these two things. You can use it to solve for that thing if you know these two things. You can use it to solve for any one of those three, given that you know the other two, from your tree diagram, from even a Venn diagram, from any kind of diagram. Does that kind of make sense to you guys? So that's about all there is to it. We just kind of got a little tired yesterday, I think, which I'm starting to feel again. So hopefully it's not going to happen here. So let's go back to the computer chips example. I'm going to need you guys to feed me information. I'm not going to write that problem down. It's just too much work. So yesterday we looked at, it's on your handout. So go ahead and read through that again real quick here. Give you a second. Okay, so if we've got three companies, then that first set of branches has like 3 sub-branches, however you want to say it, right? So we've got, what do they call company A, B, and C? Yeah, pretty boring. A, B, and C. So how much do we order from company A? 10%. Now, they didn't have to tell you these as a percentage. If you were like doing this as a real problem, would they have told you a percentage? No, they'd probably said like we ordered 17,000 from company A, and you'd have to turn it into a percentage, right? So there would be problems like that, yeah. So you said 10%? I'm going to go 0.10 then. Company B, how many we get from them? 20%. Okay. Company C we had more faith in, right? We ordered 70% from them. Okay. Then, out of each one, the reason we ordered 70% from C is because they were a little bit more reliable. What was the chance of being defective? You can just join in, Derek. Good. So company C makes how many defective ones? 0.05%.
Oh wait, no. There's 2 zeros.
0.5%. 0.5% of the decimal is 0.005, right? So then they make mostly good ones then, 0.995. Yeah. Company B, they're not quite as good. They make more defective ones. Wasn't it like 2% or something?
Yeah.
Is it 2?
Yeah, it's 2%.
Yeah, I remember. 2, so that leaves 98% of theirs were good. All right, D for defective, G for good. And company A was the worst, so I didn't order as many from them, I guess.
4%.
4%, okay. Okay, so how many outcomes are we going to have here? Well, 6, clearly. So how do you get what those are? You multiply along the branches. This is going to be 10% of 4%, which I think is that. Use your calculator, but 10% is pretty easy to do. I think that one is, I'm going to write this as percentages. And this one is 20% of 2%. I could probably do that one, but don't trust me when I'm tired. So what is that guy? What's it work out to? 0.4? Okay. So in this guy we've got 20% of 98%. That's got to be like 0.19 something. Right? And then this is going to be a very small number again. No idea what that number is. 0.35%, Tyler? Thank you. Sounds reasonable. And this is where the bulk of our chips are going to be. We have a much greater probability of drawing a C chip that is good in this circumstance because of the numbers. So I'm guessing this is like 0.5 or 6 something. 69? Okay, we've got our tree diagram down. If you have that, I mean, you're generally going to be able to get the answer, I think, as long as you know your law of probability. So what did they ask us to do, though? So they asked us something a little bit different here.
What is the probability that the computer chip came from company B?
So the probability the chip
Defective.
came...
Yeah, the defective chip, sorry.
Oh, a defective chip came from B. Yeah, that's key. Probability a defective chip was B. If it was just the probability the chip came from B, the answer would be 20%, right? But the probability a chip was defective that it came from B, how should we rewrite that? What are we given? When you do a conditional probability, you always want to start by what do you know for sure?
Given it was defective.
You're worried about or given that it's defective, right? So you want the probability it was from B given that it was defective. Always start from this part and then do that part, okay? So we want the probability it came from B given it was defective. If you look at your little law that we wrote down just a second ago, can't you just go, that's equal to what over what? You can write it as a fraction. I guess I should have my little law over here, right? So I guess I could put it back up on the board. What was our law for the probability of A and B? It was A. We have this, so divide that to the other side. So what is A in this instance? Defective. How did Tyler get that? He looked at this, he looked at that, and there you go. So, there we go. So it's going to be that divided by, oh, excuse me, put it on the top, my bad. The and on the top, right? So, B and defective over the probability that it came from company B. Okay? And even if you're not super comfortable with that law, I think it's important to get comfortable with it. But you could really just think about what's the probability that it came from B given that it was defective. Given that it was defective means your sample space is limited to what?
All the defective.
All the defective chips. So you can really just look at all those defective chips and add those up, which is this one, and this one, and take the ones that came from B out of that total, right? So that's another way to do it. Probability that it came from B and was defective, though, is which number? That one. And I guess I'm being dangerous here writing these all as percentages, so I'm going to go back to decimals since we're doing math with it. Okay, and the probability of being in B. I have something messed up here with my law.
Wouldn't it be the probability of defective?
Yeah, I do.
I was
So see, it's pretty easy to mix things up with the law. How did we know something was funky? Because we thought about the picture. I don't know if that's how Jamie caught it. Is that how you caught it? Or
No, I
you're
was
just looking at my
looking at it and I was
symbols and
like,
saying
writing
they
it
don't
wrong.
quite mesh up, right? So I was thinking, you guys see me stop there for a second? I was like, wait a second. Weren't we looking at all the defective branches? Yeah, we were. So what's the probability it was defective? That one. Plus that one. Plus that one. Another 0. So what does that come out to? You guys are going to have to tell me. So if you're on a test or something, just a worksheet, enough to write it out. But you'd say there's a 34.78% chance that a defective chip came from company B. Okay, so there you go. Just a tree diagram example. Let's look at one more before we call it quits for today. We've looked at Venn diagrams a decent amount. We'll keep looking at them this week though. We've looked at tree diagrams, so definitely need to do some more of those still. I want to look at the third thing. What was the third organizational tool or visual for computing probabilities? A table. So let's look at the other side of that guy and look at the table problem. So I'm going to get that down here. Okay, so last example for today, we're going to look at a contingency table or a two-way table. So we've got an introductory stats class, and they were asked or surveyed. I don't know what kind of surveying they did. Cluster, stratified, random sampling. I think they just tried to do everybody, but whatever. They were surveyed, we'll assume the whole class. There were obviously a lot of students here. Whoa, 331. Okay, so it must be all the stats classes at a college or something. But the first question is in regard to breakfast. What's the probability a randomly selected student is female? So we're ignoring the event breakfast. So probability female. I think we've done this before, pretty much. How do I get that? What out of what?
Female divided by
That should be easy. So what goes on top?
female.
How many?
190.
That was easy. So kind of review there. What's the probability that someone ate breakfast? That also should be easy. We're just limiting the sample space. Then we want to know, a little more interesting, the probability that they were female and ate the breakfast. And then we want to know the probability that they're female given that they ate breakfast. I think we'll do that one a couple ways. The probability they ate breakfast is what out of what?
Breakfast.
Well, there were 191 people who ate breakfast out of that same 331 people. So that's going to be 57. Okay, what's the probability they were female and ate breakfast? Where should I look in the table for that? Female and ate breakfast is here, right? So that's 125 out of the total. Still pretty easy, that's like a third about. It's about 37.8%. Now this is kind of new. You can do it with the law of probability we've been writing down. If you do, I might ask you to pause the video right now and try to write it out yourself and see if you're right. Why don't you guys try to write it out yourself? Which thing is it if you use that and law? So I'll give you a second. But really, I'm not going to even do the problem that way. I just want to show it to you in case you ever need that on a more advanced question. So it's going to be something over something. It's pretty easy to figure out that the and goes on top. It's easy to mix up though, because I did it a second ago. So the top part's easy because you just got to put the two things, breakfast and female. What goes in the bottom, breakfast or female? Female. It's really easy to mix this up because for the and, does it really matter which way you put these if it's and? No. But when you're writing it out with the multiplication rule, it really matters what's first because that's the thing that's dividing by. So if you ever get confused, just write the law out from memory, just like we thought about. Probability of A and B is the probability of A times the probability of B given that A happened, and try to match it up. That's very intuitive. This is not very intuitive. But do you really even need to think about it that way? No. Just go back to the original thing and get that really in your head. The probability that they were a female given that they ate breakfast. I'm limiting the sample space to what? Just the people who ate the breakfast. Because we're given that they ate breakfast. So these people are gone. So the total number of people then we have to worry about is 191. What's the probability they were a female given that that was true? Oh, 125. So what does that guy work out to? 65%. Okay, does that make it kind of clear? Yeah, Tyler.
Why did we switch out female and breakfast? Why did we?
Why did I switch these right here?
Yeah.
Because I was being dumb. Because it really doesn't matter if you switch these here.
Oh, no.
It just makes it a lot harder to see that the rule matches. That's what got Emma, I know.
Okay.
So, yeah, I shouldn't have done that. If I hadn't have done that, I'd have gotten it right easier from thinking about how it matches up. Well, okay, good question. Very good question. All right, so we got a couple other questions to answer. Let's do them. Next one says, what's the probability what? Oh, backwards. What is the probability that someone ate breakfast given that they were female? So this time, what are we limiting our sample space to? Well, we're given, we know they have to be a female. So we're just going to look at this. So the total is 199 now. How many of those ate breakfast? 125. So if you do that guy, you're going to get a different number, 62.8%. When we did it previously, and we're going to investigate this more tomorrow, when we did it the other way around, female given that they ate breakfast, it was a little different, right? .4%. Yeah. Pretty close, but not the same. So question F is the part that's really interesting. Does it appear that whether or not a student ate breakfast is independent of sex? We looked at female. What do we also need to look at? Male. So which one of these two things do we want to do to answer that question? Because I don't think we want to do both of them. We just want to do one with the males. Which one? Question is, does it appear whether or not the student ate breakfast is independent of sex? Think about it for a second. Which one of these do we want to do? We're given that, or do we want to think about given that they're male or given that they ate breakfast? I think male. Because if we compare these two numbers, we'll look at the probability that they ate given whether they were male or female. And if those numbers aren't really close, then are these things independent or not? No, exactly, it depends. So let's see what that number is. So this time, if we do it, I'll do it in purple. We're limiting ourselves to the males. That's just these guys, or in other words, 132 of them. Only 66 of them ate breakfast. That's 50%. Those are fairly different. So Does it seem to matter whether you're male or female if you ate breakfast? Yes. Are these events independent? No. They're dependent. It's dependent on gender here, whether you ate breakfast or not. And that's kind of some proof. Is it heavily dependent? Well, it's not a huge difference there, but is it statistically significant? We're going to start talking like that. Yes, it is.